Welcome back, students. Welcome to the lecture 4 in the series of lectures related to the design of FIR filters. In the previous lecture, we have seen the method of designing FIR filters using Fourier series. In FIR filter design, by using this Fourier series method, the infinite duration samples or the infinite duration impulse response was abruptly truncated so that we can be getting our finite duration impulse response. And we have also seen that abrupt truncation has resulted in oscillations in the stop band in the previous example that what we have seen. And this effect is known as the Gibbs phenomena. To reduce these oscillations, which are undesired in nature, generally the Fourier coefficients of the filter are modified by multiplying the desired impulse response coefficients by with a finite weighing sequence, which we call it as a windowing function. This leads to the method of FIR filter design using windows. After multiplying the windowing sequence W of n with the desired impulse response, we get a finite duration sequence H of n that satisfies the desired magnitude response. In the Fourier series method, we have abruptly truncated, whereas in this step here we multiply with a sequence called as windowing sequence. This is the only difference at what we see when compared to the Fourier series method and the windowing method. This whenever we multiply this with W of n, then we get our desired magnitude response, that is H of n, and after multiplying this we can proceed further for finding the frequency response H of e power j omega of the filter, which can be obtained by finding the convolution between HD of e power j omega and W of e power j omega, where HD of e power j omega represents the Fourier transform of HD of n, and W of e power j omega represents the Fourier transform of W of n. Based upon, since the multiplication in time domain leads to convolution in the frequency domain, the frequency response of the desired impulse response is given as H of e power j omega, which is equal to the convolution of HD of e power j omega and W of e power j omega. And so whenever we observe the relation for this H of e power j omega, the frequency response can be obtained by using this relation as 1 by 2 pi integral of minus pi to pi HD of e power j theta W of e power j omega minus theta d theta. This represents the convolution between the HD of e power j omega, the Fourier transform of HD of n, and W of e power j omega, which is the Fourier transform of W of n. Let us understand this relations by using a graphical representation, a pictorial representation. So let us consider a desired impulse response that what we obtained by applying the Fourier series, the inverse Fourier series coefficients on the given HD of e power j omega. So let us consider this is what we have obtained, HD of n. But this HD of n is generally having its values all over n from minus infinity to plus infinity. In Fourier series method, we have abruptly truncated so that we will be getting our H of n. But in windowing method, we generally multiplying with a windowing sequence, something like this, which has its values located over a finite number of n values, finite number of n. Whenever we multiply this HD of n with the W of n, this yields the exact replica of HD of n, but only over these samples from minus n minus 1 by minus of n minus 1 to minus of n minus 1 by 2 to plus of n minus 1 by 2 whenever n is odd. This is how we get our h of n, a finite impulse response from the desired frequency response that what we have considered. And the responses on the left actually shows the Fourier transforms of W of n, which is represented as W r of e power j omega. Since this takes all the values, a constant values which is equal to 1, generally I call this as a window, a rectangular window. That is the reason I show this the Fourier transform of a rectangular window here. And similarly, whenever I multiply this hd of n with w of n, I get my h of n, and the Fourier transform of h of e power j omega is shown in this figure. So, but after applying the transfer function, after finding the transfer function in terms of h of z and trying to make it causal, generally the final impulse response will appear like this from 0 to n minus 1. This is the essence of this windowing technique, that what we do. Actually, the Fourier transform of a window consists of this, what is called as a central lobe. This is what I call as a central lobe from minus 2 pi by n to 2 pi by n, and the other lobes are called as central side lobes. These are called as the side lobes. Central lobe or the main lobe, this is what we call as, and these are called as the side lobes. The central lobe of this windowing function or the main lobe actually contains most of the energy of the window, and the frequency response of this particular impulse response mainly depends upon this windowing response only, the frequency response of the windowing filter only. Therefore, the window filter that what we choose for truncating this infinite impulse response should have some desirable characteristics. They are the Fourier transform. As I said, I have just the frequency response depends upon the frequency response, and therefore the window chosen for this and the desirable characteristics are: the central lobe of the frequency response of window should contain most of the energy and it should be narrow. Okay, as shown in the figure, it should contain most of energy in this main lobe itself, and it should be as much as narrow as possible, and it contains most of the energy of the window. And the frequency response of the filter and the highest side lobe level of the frequency response should be small. And whenever you compare, generally the desirable characteristics of a window are the side lobe level, the first side lobe level, that is what we consider. The amplitude of this side lobe level should be as small as possible, and the side lobes of the frequency should decrease in energy rapidly as omega is tending to pi. Okay, and whenever it is the side lobe level should energy should be decreasing as shown in the figure, as is omega tends to pi in the frequency response. Omega tends to infinity in the frequency response. And based upon these characteristics, there are different types of windowing sequences which we will be discussing in this lecture, and they are listed here. 6 windowing sequence primarily we are going to discuss in our lectures, and they are the rectangular window, Bartlett or triangular windows, Hanning and Hamming windows, which are called as raised cosine windows, Blackman window, and a Kaiser window. Okay, we are going to primarily discuss about these 6 windows in the coming topics, and let us start our discussions with rectangular window. The n-point rectangular window WR of n is defined as WR of n is equal to 1, for all n from n minus 1 by 2 to plus n minus 1 by 2, and it is 0 for all other values. So whenever we have the odd values of n, generally we use this particular equation for this windowing sequence. Alternatively, whenever we would like to represent the windowing sequence for both the values, both odd and even values of n, generally we use this definition: WR of n is equal to 1 for n is equal to 0 to n minus 1, and it is 0 otherwise. And when we calculate the Fourier transform of this WR of n from minus n minus 1 by 2 to plus n minus 1 by 2, generally the Fourier transform or the frequency response of this rectangular window is resulted with this particular expression: sine of omega n by 2 by sine of omega by 2. You can just find out this frequency response by using this equation and expressing it in the using those geometric series sum formulas, as well as exploiting the sin theta representation in terms of exponentials and all. You will be able to get this particular expression comfortably. And based upon this magnitude response, the frequency response that what we got, I would like to represent the magnitude response of the rectangular window as well as a log magnitude response of the rectangular window. In the figure, the topmost figure actually shows you the rectangular windowing sequence, which has its values: capital N is equal to 31, which is odd in nature but evenly spread with a center of symmetry at 0 from minus 15 to plus 15. It contains a total of n is equal to 31 samples. And the magnitude response of this rectangular windowing sequence is shown in this figure, and this is what I call as this main lobe of this windowing sequence, and these are the respective side lobes that what we observe here. And whenever you generally observe the spectrum, the main lobe width that what we are considering here, the main lobe width is nothing but the distance between the 2 points that is closer to omega is equal to 0, and where the magnitude of WR of e power j omega in dB is 0. Okay, these are the points generally where we generally observe that it is almost 0 here. Okay, it is almost 0 here, which is almost equal to 0.05. That is the reason I show this is a main lobe width size, and it is equal to 4 pi by n in the case of a rectangular windowing sequence. And similarly, the maximum side lobe amplitude for WR of e power j omega occurs for the first side lobe and is equal to minus 13 dB approximately, and it is shown in this log magnitude response, which is approximately equal to minus 13 dB. This is a amplitude of the first side lobe, that is what observed in this log magnitude response of the rectangular window. Log magnitude response is nothing but that what we represent the magnitudes in terms of 20 log of this magnitudes. Okay, 20 log of these values are represented, and this is what I call as a log magnitude response. The approximated filter responses actually differs from the ideal desired responses in several ways, and whenever we see there is a sharp transition in the ideal response at omega is equal to omega c, but here we were able to see that there is a gradual transition, and in the pass band a series of overshoots as well as undershoots also occur, and in the stop band the ideal desired response is 0, but the FIR filter has a non-zero response. And this is what we call as leakage. Actually, I would like to explain these kind of terms with respect to the magnitude response of a low pass filter, FIR filter designed using this rectangular window. And whenever we design a low pass FIR filter using rectangular window, this is for n is equal to 31 and cutoff frequency is equal to 0.5 pi radian per sample, that is simply pi by 2 radian per sample. In such case, the magnitude response is something like this, and the log magnitude, the corresponding log magnitude response is shown in this figure. And whenever we observe this, this is what I call, generally what should happen is there should be a sharp transition with respect to the ideal frequency responses, but here we do have a gradual transition, and this is what we call as a transition band. And in the pass band, a series of overshoots as well as undershoots also occur, and in the stop band also ideal response is generally 0, but you are able to see that there are some non-zero responses, and we call this particular thing as a leakage. The main lobe of this WR of e power j omega actually causes the main lobe, that what we see in the windowing function, the frequency response of the windowing function causes a smearing, this kind of smearing in the desired transfer function features. And the width of the transition region, that what we see, the width of the transition region, the 4 pi by n, that what we see in the width of the transition region, that what we see in the frequency response is related to the width of this main lobe, that is equal to 4 pi by n in this case. Okay, the width of the transition region is related to this main lobe width of WR of e power j omega, and since the main lobe width WR of e power j omega is equal to 4 pi by n, the size of its transition region can be reduced to any desired size by increasing the size of n values of the windowing sequence. But however, whenever we increase the value of n, it also increases the number of computations that are necessary to actually design or implement that filter. And similarly, whenever we see the side lobes of our WR of e power j omega, the side lobes, they are extended over a frequency range, over a large frequency range, over a wide frequency ranges, and this large magnitude components in HD of e power j omega, they becomes smeared over a wide range of frequencies in H of e power j omega. In H of e power j omega, and in the pass band, the side lobe effects appear both as overshoots as well as undershoots to the desired responses, and but in the stop band, these effects appear as a non-zero response. That is what we were saying. Generally, it should be 0, but it is a non-zero response. These side lobe effects do not diminish significantly, but remain almost constant as the duration of this rectangular window is increased whenever. Therefore, it is observed that whenever the number of elements of HD of n included in the H of n, the magnitudes of the overshoot as well as leakage will not change significantly, and when the rectangular windows are used, and this result is known as Gibbs phenomenon, after that great American mathematician J.W. Gibbs of Yale, who first noted this effect. To reduce his side lobe effects, we generally consider alternate windowing sequences which has spectrum exhibiting smaller side lobes. Okay, and therefore we now move to this another windowing sequences from this disadvantage of rectangular window, and we call it as a Bartlett or a triangular window. The triangular window have been chosen such that it has tapered sequences from the middle on either sides. It has tapered sequences from the middle on either sides, and the endpoint triangular window is generally defined as Wt of n is equal to 1 minus of 2 mod n by n minus 1 for the values between minus of n minus 1 by 2 to n minus 1 by 2. Alternatively, whenever we are choosing the windowing sequence that gives that is apt for both odd and even values of n, generally we use this particular definition: Wt of n is equal to 1 minus of 2 modulus of n minus 1 by 2 by n minus 1 for n is equal to 0 to n minus 1, and it is 0 otherwise. And similarly, whenever I find the frequency response or the frequency spectrum of the triangular window, Wt of e power j omega, it is obtained by the by taking those Fourier transform of the triangular window sequence Wt of n, and I obtain it as sine of omega into n minus 1 by 4 by sine omega by 2 whole square. And let us observe the magnitude response and the log magnitude response of the Bartlett window, that what we have calculated here from the frequency response. And for the same number of points that what we have calculated in the case of a rectangular window, I would like to have to compare between with this triangular window and this rectangular window. I have calculated the magnitude response for the same number, n is equal to 31 here too. And whenever I see in log magnitude response of the triangular window, the first side lobe level is smaller than that of rectangular window whenever we compare them, and it is being reduced from minus 13 dB to minus 25 dB in this case. But the main lobe width in the case of rectangular window was 4 pi by n, but here it is 8 pi by n, which is twice that of our rectangular window for the same duration for n is equal to 31. Actually, these results suggest that whenever we choose a triangular window, there is a triangular window or a rectangular window, then there will be a trade-off between the main lobe width and the side lobe levels. And whenever we compare the magnitude response and the log magnitude response of a low pass FIR filter, which is designed using a triangular window, we observe that the triangular window produces a smoother magnitude response for FIR filter. It produces a smoother smoother magnitude response here in this case when compared to this particular response in the case of a rectangular window. And whenever we see the transition from pass band to stop band also, this is not that much steep as that what we have seen in the case of rectangular window. In the stop band also the response is smoother, but the attenuation is less than that what it is produced in the rectangular window. Whenever we compare with those values, this is not less when compared to that of the rectangular window, and here there is a much more attenuation. There is the values are not attenuated actually, and therefore these characteristics of this triangular window generally these characteristics generally doesn't make a good choice for choosing this particular triangular window over a rectangular window. That's the reason we move for another particular windows which brings a motivation for the development of another class of windows called as raised cosine windows. We'll try to discuss about this raised cosine windows, specially called as Hanning and Hamming windows, in the coming classes, and that's it for this lecture. Thank you.